17.4 Series Solutions. Many differential equations can't be solved explicitly in terms of finite combinations of simple familiar functions. This is true even for a simple looking equation like equation 1 y double prime minus 2xy prime plus y equals 0. But it is important to be able to solve equations such as equation 1 because they arise from physical problems, and in particular in connection with the Schrödinger equation and quantum mechanics. In such case, we can use the method of power series, that is, we look for a solution of the form y equals f of x equals the sum from n equals 0 to infinity c sub n x to the power n equals c sub naught plus c sub 1 x plus c sub 2 x squared plus c sub 3 x cubed plus ellipsis. This method is to substitute this expression into the differential equation and determine the values of the coefficients c sub naught, c sub 1, c sub 2. This technique resembles the method of undetermined coefficients discussed in section 17.2. Before using power series to solve equation 1, we illustrate the method on the simpler equation y double prime plus y equals 0 in example 1. It's true that we already know how to solve this equation by the techniques of section 17.1, but it's clear to understand the power series method when it is applied to this simpler equation. Example 1. Use power series to solve the equation y double prime plus y equals 0. Solution: we assume there is a solution of the form equation 2 y equals c sub naught plus c sub 1x plus c sub 2x squared plus c sub 3x cubed plus ellipsis equals the sum from n equals 0 to infinity of c sub n x to the power n. We can differentiate power series term by term, so y prime equals c sub 1 plus 2 c sub 2 x plus 3 c sub 3 x squared plus ellipsis equals the sum from n equals 1 to infinity of n times c sub n to the power x. That is the sum from n equals 1 to infinity of n times c sub n times x to the power n minus 1. Equation 3, y double prime equals 2 c sub 2 plus 2 times 3 c sub 3 x plus ellipsis equals the sum from n equals 2 to infinity of n open n minus 1 close c sub n times x to the power n minus 2. In order to compare the expressions for y and y double prime more easily, we rewrite y double prime as follows. Equation 4, y double prime equals the sum from n equals 0 to infinity of open n plus 2 close open n plus 1 close c sub n plus 2 x to the power n. Substituting the expressions in equations 2 and 4 into the differential equation, we obtain the sum from n equals 0 to infinity of open n plus 2 close open n plus 1 close c sub n plus 2 times x to the power n plus the sum from n equals 0 to infinity of c sub n times x to the power n equals 0. Or equation 5, the sum from n equals 0 to infinity of open bracket open n plus 2 close open n plus 1 close c sub n plus 2 plus c sub n, close bracket, x to the power n equals 0. Sidebar. By writing out the first few terms of equation 4, you can see that it is the same as equation 3. To obtain equation 4, we replaced n by n plus 2 and began the summation at 0 instead of 2. Back to the text. If two power series are equal, then the corresponding coefficients must be equal. Therefore, the coefficients of x to the power n in equation 5 must be 0. Open n plus 2, close, open n plus 1, close, times c sub n plus 2 plus c sub n equals 0. Equation 6, c sub n plus 2 equals negative c sub n over open n plus 1, close, open n plus 2, close, n equals 0, 1, 2, 3, ellipsis. Equation 6 is called a recursion relation. If c sub naught and c sub 1 are unknown, this equation allows us to determine the remaining coefficients recursively by putting n equals 0, 1, 2, 3 in succession. Put n equals 0, c sub 2 equals negative c sub naught over 1 times 2. Put n equals 1, c sub 3 equals negative c sub 1 over 2 times 3. Put n equals 2, c sub 4 equals negative c sub 2 over 3 times 4 equals c sub naught over 1 times 2 times 3 times 4 equals c sub naught over n factorial. Put n equals 3. C sub 5 equals negative c sub 3 over 4 times 5 equals c sub 1 over 2 times 3 times 4 times 5 equals c sub 1 over 5 factorial. Put n equals 4. C sub 6 equals negative c sub 4 over 5 times 6 equals negative c sub naught over 4 factorial times 5 times 6 equals negative c sub naught over 6 factorial. Put n equals 5. C sub 7 equals negative c sub 5 over 6 times 7 equals negative c sub 1 over 5 factorial times 6 times 7 equals negative c sub 1 over 7 factorial. By now we see the pattern for the even coefficients. C sub 2n equals open negative 1 close to the power n times c sub naught over open 2n close factorial. For the odd coefficients, c sub 2n plus 1 equals open negative 1 close to the power n times c sub 1 over open 2n plus 1 close factorial. Putting these values back into equation 2, we write the solution as y equals c sub naught plus c sub 1 x plus c sub 2 x squared plus c sub 3 x cubed plus c sub 4 x to the power 4 plus c sub 5 times x to the 5th power plus ellipsis equals c sub naught open 1 minus x squared over 2 factorial plus x to the 4th power over 4 factorial minus x to the 6th power over 6 factorial plus ellipsis plus open negative 1 close to the power n times x to the power 2n over open 2n close factorial plus ellipsis close plus c sub 1 open x minus x cubed over 3 factorial plus x to the 5th power over 5 factorial minus x to the 7th power over 7 factorial plus ellipsis plus open negative 1 close to the power n times x to the power 2n plus 1 over open 2n plus 1 close factorial plus ellipsis close equals c sub naught times the sum from n equals 0 to infinity of open negative 1 close to the power n times x to the power 2n over open 2n close factorial plus c sub 1 times the sum from n equals 0 to infinity of open negative 1 close to the power n times x to the power 2n plus 1 over open 2n plus 1 closed factorial. Notice that there are two arbitrary constants, c sub naught and c sub 1. Note, we recognize the series obtained in example 1 as being the Maclaurin series for cosine x and sine x. See equations 11.10.16 and 11.10.15. Therefore, we could write the solution as y of x equals c sub naught cosine x plus c sub 1 sine x. But we are not usually able to express power series solutions of differential equations in terms of known functions.